Hello, in this session we are going to talk about axial rods in tension or compression when the cross-sectional area is changing. We're going to look at one example here where the cross-sectional area is changing in a linear fashion. So we have a rectangular cross-section at the top with a rectangular cross-section on the bottom. They both have the same thickness, but the width is increasing as we go down or decreasing as we go up. The bar, the rod is fixed here at the bottom, and we have a point load acting here at the tip in either tension or compression. And we're interested in determining how much this deforms due to the application of in this case, the compression load. Could be tension, the result could be the same, except in the opposite direction. So here we see that the width changes as a function of x, starts at b1 minus b1 minus b2 divided by L, which is the length of the rod, times x. So you can see when x equals to 0, b is b1, and when x equals to L, the L's cancelled, b1 minus b1, and then you get b2. So it's a linear variation that looks something like this, right? B plus ax. So how do we solve this problem? So basically, to solve this problem, we have to extend the concept that we have already explained related to the rods in series, right? So what we have here is basically an infinite number of rods in series. Each one of them has a different area. It has a differential length and is subjected to the same force. So if we start with our basic equation that says PL over AE, now in this case L is going to be dx. And since we know that when they are in series, basically the deformations add, so our formula is going to be that the total deformation is going to be the sum of P times dx divided by A divided by E. E is the elastic modulus and A is the cross-sectional area, which in this case varies as a function of x. P is constant because the axial load is constant throughout the height, assuming that we neglect the self-weight of the rod. We are going to deal with that later. And so this integral is our key equation to solve this problem. So let's write it down here. Basically say delta is the integral from 0 to L P dx divided by E times AX plus B. It's sort of the generic form of the variation of the area, right? This is area as a function of x. P comes out as a constant, E comes out as a constant, and then if we would like, right, we can simply integrate this directly, dx ax plus b. Now the key here is to solve this integral. And if you remember from calculus, the solution to that integral is some kind of log, right? Because it's the integral of sort of dx over x in some linear change of variables. So actually, the exact expression goes something like this: p over e times 1 over a times the log of ax plus b. And that must be evaluated between 0 and L. So now we just simply need to repopulate A with this, B with this, plug it back in here, and get the final expression. If we do that, this is what we obtain. P. So A is this term. So there is a minus term that comes in here. We have E. And here, keep in mind that we do need to multiply by h, so to get an area, right? This is the variation of the width. To get an area, we need to multiply by h. So this becomes E times h times B1 minus B2 divided by L, so that L comes upstairs here. We've taken care of this 1 over A, and then we need to say log of A, which is minus B1 minus B2 divided by L, evaluated at L, plus B, which is plus B1, minus log of this evaluated at x equals to 0. In this case, we simply get minus log of B1, because this A times 0 doesn't appear anymore. So these L's cancel. Oops, put this here. These L's cancel. And we get minus P times L E H B1 minus B2 times the log. So here we get minus B1 plus B2 plus B1. So this becomes log of B2 minus log of B1. Now, if we remember from logarithmic identities, this is the log of B2 divided by B1. And we can continue to modify the equation to look a little more consistent. And so I'm going to do a couple of things here. So I'm going to substitute this by its mathematical identity, log of B2 divided by B1. That's by the law of logarithms. And this here, I'm going to simply multiply and divide by B2. So I haven't changed anything, but this B2 divides these terms, and we end up with a really nice expression here that looks something like this. Well, one small change before we do that. You see this minus sign? I'm going to bring it in here. And so this will actually be B1 minus log of B2. So then this becomes log of B1 divided by B2. And here when we do this, we will have E, H, B1 divided by B2 minus 1 times B2, all of that times this log right here, right? So if we just reorganize that and let's call this coefficient alpha B1 divided by B2, which is basically the ratio of the two widths, right? How bigger is B1 with respect to B2? If we do that, we get this really nice expression here that says PL, there is no minus here because we've already integrated it with the expression, PL over E H B2 times log of alpha divided by alpha minus 1. And so you can see here that we basically have two parts to the deformation. PL divided by EH B2, which is basically the deformation as if we would have just used the top area, times a coefficient that has to do with the ratio of the areas, and that in this case is going to be less than 1. And the reason